Cool. All right. So this is one way that we could talk about containerization. And then I'm going to talk a little bit about Kubernetes as a container orchestrator, just because this is useful information just to have in your back pocket. So this is from building and deploying microservices on EKS, which is the Elastic Kubernetes Service. It's one of the 2 platforms that is purpose built for containers. This is not a joke, but I just have to tell you this, is that I think there are currently 33 ways to run Docker containers on AWS. Like Lambda will take containers, Beanstalk will take Docker containers. So there was a post by a gentleman named Corey Quinn, which was like 17 ways to run containers, part 1, and then he wrote a part 2, and then someone told him that, hey, one of those ways is actually a duplicate, and he was like, okay, I stand corrected. There's 33, not 34 ways to run containers on AWS. Some of it's weird, like IoT and EC2 and like stuff like that. But so the thing is then what are containers, right? Like why do we like talk about containers? So when we build applications, obviously we're looking for particularly horizontal scalability, obviously being cloud deployable, or really honestly anywhere kind of deployable, which to a certain extent containers grant that. Making sure they're in a declarative format, meaning I want the end state to be reproducible every time and idempotent, right? And now what's interesting about this is that, Amazon put declarative format in here, and just so you know, building containers is very procedural. So it's do this, do this, do this, and do this. It's not, hey, I want a square with, black edges and stuff like that, and I want it in this position. It's, I don't care how you get there or how you draw it. That's more declarative. Containers are remarkably procedural. So it's kind of funny that they do that. So the container fundamentals is that this is basically about, this is no different than what you already know. And let me clarify what I mean by that. Containerization is nothing more than process virtualization. It's application virtualization. That's all it is. Now, people will compare them to virtual machines, which they're not, but that doesn't mean, by the way, there isn't like virtual file systems and there's not virtual networking. There is. But the thing that I don't like the virtual machine comparison is that you actually don't run a kernel inside of a container. People will be like, but wait, Michael, I run Ubuntu. I know it looks like you're running Ubuntu, but you're actually just running the binaries, right? You're not running a kernel inside the container. You're using the host kernel. So what happened is that before containerization came along, we had as many frameworks for deploying and packaging applications, at least as there were languages. Java packages and deploys differently than the way .NET does, than JavaScript versus Node versus, like the list goes on and on. And so it's no different than the problem we had with like shipping containers with like ships, where like, they're basically saying, hey, how do we create a sense of standardization if I'm shipping like bananas versus like tires versus something else? And the catch here is that we were looking for a way to not necessarily change the languages. Like, I don't want to like change bananas. I don't want to change tires, right? I don't want to change clothing when it gets shipped in a shipping container, but I want to put it into a format that if I know how to deal with the format, then no matter what's inside the box, I can deal with the box, right? And this is what shipping containers got us, right? So in about, I think it was like 1958 when Malcolm McLean and a guy named Tentlinger, they like patented the current international shipping container, right? So this basically improved handling on both ships, trucks, and import, because now as long as you had the infrastructure to deal with the metal container that gets wrapped around your goods, as long as you knew how to deal with that, you didn't care what was inside. You knew how to ship tires, you know how to ship bananas. And don't get me wrong, inside the container, there's probably some like provisions for how to like cool the bananas to make sure they don't rot. There's probably another provision for how to like stack the tires so they don't roll around. Not that you were worried about them being damaged, but you get the idea. And so whether it was truck, rail, ship, or whatever, once we had shipping containers, things became really easy because all you needed then was the infrastructure to deal with containers. You didn't have to have the infrastructure to deal with bananas, tires, clothing, etc. Everybody follow me thus far? So what if we did the same thing with software? What if we took Java, .NET, Ruby, Python, Rust, Erlang, Golang, whatever. We took it and we put everything we needed to run and ship that language or that application, right? Because it's written in a language, so it's really the application. What if we could standardize, like put a wrapper around it so that as long as you knew how to deal with the wrapper, you didn't care if it was Java inside, or you didn't care if it was .NET inside, you didn't care if it was Ruby. Because everything that the application needed to run was inside the container. And so all you needed to do was just execute the container's instructions, in this case, the shipping container's instructions, and you were good to go. It would run. Now, don't get me wrong, shipping containers need to be on ships, on trucks, and on rail. In other words, you need to have some common infrastructure in order for these containers to work. What do I mean by that from a software perspective? If you compile a binary in Go and that binary is compiled for Windows and it's inside of a container, that container needs to run on Windows. If it's compiled for Linux, then it needs to run on a Linux host. So all this is process isolation and process virtualization. This is just application isolation and application virtualization. That's all this is. And so we're used to running applications on bare metal servers and in virtual machines. But I want you to notice that in this particular case, I've got an operating system down here. I've got a virtualization platform, and then I've also got guest operating systems that get duplicated every time I launch an application because I'm creating new virtual machines practically for every app. If I'm lucky, I'm going to stack the database and the application all in the same box, maybe, but that's like bad practice because then you got things tightly coupled. So quite frankly, you're going to have basically an instance of that guest operating system for every instance of your application. In other words, if you want your monolithic app to scale to 10 boxes, you're going to have 10 copies of the guest operating system. We've been doing this for 20 years. This is how we've been using virtual machines, right? One app, one operating system. Now, the virtualization platform is probably going to be VMware, but it could also be Hyper-V, it could be Xen. And in that case, by the way, the virtualization platform and the operating system kind of munge together, right? That's why we call them hypervisors. Is this unfamiliar to anybody? Is anybody like, I'm completely lost, Michael? Why are we talking about this? Is this not the way we've been doing things for the last 20 years? I'm gonna take your lack of interaction as assent, right? Either that or I'm not coming through. No, looks like I am sending signal. Okay, so this is the way we've been doing it. What if we could get rid of the operating system? What if we could just let the operating system go? What if instead of having to replicate the guest operating system every time we want a new instance of our application, what if instead we could just not do that? What if instead we could come up with a standard containerization platform that runs on top of an operating system? So just make sure we're clear, we still need virtual machines because this whole thing could be a virtual machine now, right? But what happens is that instead of running one app per one guest OS, what we can do instead is that now we're running multiple applications that are isolated from each other on the same virtual machine. How many applications can you get on one virtual machine if you're doing this? Well, it's not hard coded, but typically you can get 100. If you're using OpenShift or something that's been modified, you can get 200, but out of the box, Kubernetes will usually host about 100 containerized applications on a single operating system. So this means, and by the way, this is a little bit of a misnomer because you wouldn't actually like share libraries between containers unless you really had to, or the libraries were like super big. These would all be isolated from each other. They would run independently. So this is a little bit of a misnomer because you wouldn't share libraries among these systems. And so what this means is that now I can run, 100 containers on top of this single operating system right? And they're going to be isolated from each other. I can have multiple versions of Java, multiple versions of Ruby, multiple versions of .NET all running side by side, and they're not going to see each other because the containerization platform is going to isolate those containers both from a file system and a networking perspective away from each other. They're going to have their own isolated process space, their own isolated memory space, give or take, and their own isolated networking and storage, right? They're going to have their own isolation. So what happens is that you've now got, you have eliminated the replication of the guest OS every time you want to launch an app. That's gone. No more guest OS replication. So containers, by the way, since they don't have an operating system inside of them, don't get me wrong, they can have operating system binaries, but they're actually not running a kernel. What's happened now is that you now have it so that you can run 100 of these things, and they're like 30 megs in size or 100 megs in size. They're not 4 gigs in size or 2 gigs in size because they have a full operating system inside of them. So this is what containerization is. It's taking your Java app, sticking it into a standard portable deployable format called a container. And that container can now be run on any other operating system that has the same processor architecture and the same operating system, and it's got the containerization software. In other words, if you make a Docker container, just as an example, you probably need the Docker engine to run, or something that's like what they call like OCI compliant, right? So something that has a container runtime that can actually handle a Docker container, which there's a deeper discussion there, but we're going to leave that alone. So the point being is that if once you have the containerization platform on your operating system, you can then run the container in question. Now, this is totally fine if you're running one box and it's your laptop and you're going to run a bunch of containers on there and kind of feel it out. But just so you know, if you have to run this on 1,000 boxes, which Kubernetes, by the way, out of the box will create a cluster of 5,000 boxes if you want it. You can't run this on 5,000 boxes manually. You can't run this on 100 boxes manually. You need what's called a container orchestrator, which is what I'm going to talk about next. But the core concept here is that your application is going to go right inside, right here on this container. And so the goal here is that your application's here, maybe your other app is here, and these are totally isolated from each other inside of a single operating system. Now you might say, Michael, why would we do that? Because doesn't that add a little bit more complexity? Because before I just had an operating system and then I had a virtualization platform. Well, in some cases it reduces complexity because now you don't have another guest operating system that you have to deal with at this layer, but it does increase complexity somewhat because now you have to learn this software. You have to learn Docker and, well, containerization, and you might have to learn a container orchestrator. So hold on, Gerald, say that out loud. What is it that you're not tracking? Because now's the time.
So when you mentioned the guest operating system, and I understand that the virtual machine has this operating system that each application is using, but when you're saying that now there's a guest operating system, I'm not quite tracking that.
So if you go into a data center, which has VMware installed on all the hardware, that's this level. That's the virtualization platform and the operating system at the hardware level, sitting on top of the server hardware. When you then go to IT and say, hey, I need 50 Windows boxes, that's all guest operating systems on top of this hardware.
Okay.
Right? When you go to EC2 in AWS, they run a modified Zen hypervisor. That's the virtualization platform for virtual machines. When you go in and spin up 50 Windows boxes, those are all guest operating systems.
Okay.
Yeah. So anytime you're running a virtual machine, the operating system that's in there is called a guest OS because it's actually not the host, it's the guest.
Okay, I see where you're going with that.
Yeah, the host is the one that's talking directly to the hardware. The virtual machines are not talking directly to the hardware. They're actually talking to the host.
I see.
Yeah.
Okay.
So what happens is that now you no longer need to replicate a guest OS because you got containers that are actually isolating basically the applications or processes from each other. And so all you really need is the containerization software and one operating system that's talking to the underlying hardware. Now, this is where it gets a little tricky because this is a little weird, is that you can actually run the containerization software directly on server hardware. But just so we're clear, most of us are actually going to take this picture right here and we're going to take it and we're going to run it inside of a virtual machine, just so we're clear. So it's an on cloud at least, right? But you could do this in your data center. You could run the containerization software directly on your hardware. So virtual machines are still at play, but the thing that changes is the density of applications. So now instead of having just one app running on the virtual machine, you can now have 100 apps running on the virtual machine as long as you have the resources for it. You might say, well, Michael, how can you get away with running more applications? Well, because you're not replicating the operating system. You're not replicating the operating system along with the application. You're only replicating the application. You're making copies of the application. You're not making copies of the application and the operating system that goes with it. So this is why you can get more applications with containers onto a box, because you are not copying the guest operating system every single time you deploy an app. So that's the distinction. Now,
How is this?
Go ahead.
How is this different than, let's say, a time slicing? Back when Windows came out, let's say you can run 10 applications at the same time, and you can time slice it, give 10 nanoseconds to this, 10 nanoseconds to that, 10 nanoseconds, and they keep going in loop like that. How is this any different? This sounds like the same thing to me, except it's in the cloud.
Well, this isn't in the cloud. You can run this anywhere, Gerald. So the difference is that Windows doesn't isolate those applications from each other. They can easily mess with each other. If one crashes, the system, you can crash the whole box, right? Containers are isolated from each other, right? They're in their own process and memory space. Now, don't get me wrong. If they crash the host, they could potentially crash everybody, but that's really hard to do in this level of isolation. So, and to be clear, this is mainly Linux-based containerization. Windows-based containerization operates similarly, but is a little less mature, right? If you're familiar with like BSD, for example, and actually Adam just mentioned the same thing. If you're familiar with BSD, any of the old style Unixes, or even mainframes, by the way, they'll do the same thing where you can actually isolate and jail processes so you can't mess or talk to or even see other processes outside of your particular namespace and or control group. So this concept has been around for a long time. Windows by far was not the first to even approach this. But the thing you're talking about where you could like nanoslice and apply like scheduling and isolation, it doesn't do the same level of security isolation. So it's a very different beast from the way Windows did it like way back when. This is actually closer to BSD jails, or if those of you who worked on Sun Solaris back in the early 2000s, this is Solaris containers. But Docker as a company was the first to make it easy, right? And that's what changed everything, is that they made it easy to do. It was a little harder to do back then. So once it's in a container and it's isolated, first of all, you do get a certain measure of portability, meaning you can now run multiple Javas at the same time and you don't have to worry about them interfering with each other. You can now run multiple Ruby versions at the same time and you don't have to worry about them interfering with each other because they're in their own isolated process space. They're not going to reach for the same files. They're not going to see the same file system. They're not going to have the same networking. They're not going to have the same storage, right? So this also, by the way, allows us to scale them horizontally quicker and faster because they're now smaller, no guest operating system. So smaller, just the application. And then allows us to distribute them across a wide number of boxes as well. Because containers are inherently immutable, the container images that like you deploy, the images are immutable. It also makes oddly enough, deployability and versioning a lot easier because you don't change a running container, you redeploy a new one. This has even been backported. This is called immutable infrastructure. This has even been backported into virtual machines. Even the concept was so popular where people are like, I'm going to create an image of my virtual machine and boot off of that image. If I need to make a change to the virtual machine, I change the image and then boot another virtual machine. Now, all of that works great, by the way, until you get to data stores, databases, and whatnot. Then there's some challenges. But regardless, there's ways around that. Now, containers are great for microservice architecture because you're going to actually end up with smaller applications that are going to scale horizontally and independently from each other. So, you know, it lends itself, like containers and microservices architecture go together like peanut butter and chocolate. Each is good by itself, right? Peanut butter is good by itself, chocolate's good by itself, but you put them together and they can blend really well. So that's the core concept around containers. So other things to know is that, you know, just to make sure this is super clear, containers are going to rely very much on the host operating system's kernel because they are not running their own kernel. So just something to be very clear about is that you have your own operating system kernel in each of these virtual machines, but when you use containers, they are reliant. This is why, by the way, the processor architecture and the operating system type must match for what the container was built for. Now, if you have an interpreter for that, that's fine. But my point being is that if you build your Python app and somehow you've got stuff hard-coded in there for Windows, it's got to run on a Windows box. You can't run it on a Linux box, okay? Because it's built for Linux, it's got to be on a Linux box. If it's built for Linux x86 and you decide to run it on Linux ARM, it's not going to work unless you've got an interpreter in there for ARM. It is going to require you to run the container on the operating system and the processor architecture that it was built for. So that limitation still exists. With that in place, though, by the way, they're still ridiculously portable. So, okay, with that in mind, quick question for you. What's the difference between containers and virtual machines? A, B, C, or D? Yeah, so containers, by the way, are going to boot faster, so A is not true. Every container is going to go through a full operating system boot up. Well, that's not true because there's no operating system in a container. Containers require you to keep the versions of your libraries in sync with your applications. That's not true. They don't actually require you to keep them in sync. But I mean, to be honest, they are going to be kept in sync. So it could. Virtual machines are no different, by the way. Virtual machines also required you to keep your libraries in sync with your applications. So it's not like containers are different in that way from virtual machines. But containers sharing the underlying host OS kernel, yeah, they do. All of the containers are going to be isolated, but when they make system calls, they're going to make those system calls against the underlying host kernel. So they do require, like, you know, the kernel to match what they're going to make calls for. Okay. So here's some thoughts about a container. When we build Docker containers in particular, we use what's called a Docker file. That spelling, by the way, is accurate. Capital D, O-C-K-E-R-F-I-L-E. That's important because by default, the Docker command, when you do Docker build, is going to be looking for a file that has that spelling. So don't worry, you can put a -f on there if you want to change the file name to something else. But just know that it's going to expect what's called the Docker file. Now, here's the funny thing about a Docker file. A Docker file is used to build a container image, which quite frankly is not much different than a virtual machine image. Images are used to boot systems and bring them to life. Like, you run an image to make a container. You run a virtual machine image to make a virtual machine, right? So container images are composed of like instructions that are inside this Docker file. This is a read-only template with procedural instructions for how to source and create a container image. Each instruction, like copy, add, you know, from, run, entry point, command, like all that, there's only like 20 or 30 of them, just to be frank about it. Each instruction that's in here, especially if it changes the container or images file system, is going to basically add a layer to the system. And so what happens is that these container images are actually just stacks of change layers that have been put on, like they've been squeezed together like a pancake stack to make a container image. You might be like, Michael, why would you actually like make every change, every addition to the container image a layer? Because then, by the way, you only have to download the layers when things change that have changed. If you've got a stack of pancakes and the top one's vanilla, you got chocolate and you got strawberry, and you decide to change the strawberry one, right, to peach, for whatever, then all you need to do is download the Peach layer because the rest of them are the same. Now, to be clear about that, that's kind of a misnomer because if you change a foundational layer, it typically changes all the layers after it. But regardless, you get the general idea, right? Is that this allows you, by the way, when you download a container image to only download the pieces that you don't already have. Because oddly enough, container images work like a Git repo. There's like a primary repository, like the remote repository that has all of your like core files. And when you download a container image from a remote repository, you download a copy of that image. If that image has 7 layers and you already previously downloaded 5 of those layers, you're just going to download the 2 that need to be changed to get the new version of your container image. So container images are comprised of these different layers. Each of these instructions that are inside the Docker file make this container image what it is. And a running container is just a container image that's been told to go. I want you to run now. Now, what is the container going to do? Well, what were the instructions inside of the Docker file? Now, by the way, a lot of the instructions you can override. So at the time that you launch a container, you can actually sometimes, like most of the time, actually give it overriding instructions, right? So, so a running container, a running container is nothing more than a container image that's been told to start. How many containers can you run off of a single image? How many resources do you have? You want to run a million copies of this container image across 5,000 boxes? Could you actually do that? Let's think about that for a second. 5,000 times 100. Nah, wouldn't quite get there, but close. So, and by the way, when you launch a container image and you make it a running container, meaning that process inside the container is now running. So let's say this is a Java container image, and you run the container, you're now running the Java that's inside the container. So if it's like a Tomcat or, a jar file, war file, ear file, whatever, you're now running it. And here's what happens is that the container image is now booted up. Like the Java process is now booted up in a sense and made to run. And what happens is that the containerization software puts a thin read-write layer that's ephemeral. It's temporary. It puts it on top of the container. So that way, when the Java process like writes logs or whatever, it has like a temporary file space where it can stick stuff. Now, it doesn't look temporary to the Java process that's inside the container, but it is actually temporary because if that container crashes or, stops and goes away, is deleted, all that data is gone. Now you might be saying, Michael, what? Wait, are you saying that containers are stateless? Yes, I'm saying that containers are stateless. Don't worry, they have a temporary file system that they can write to. But once that container is deleted or stopped, it's gone. The information's gone, right? Stopping, by the way, doesn't necessarily delete it, but terminating obviously does. If the container crashes, obviously it's gone as well. Now you might say, well, Michael, what about databases? This sounds like this is just built for stateless. Well, here's the cool thing. Even with Docker, which is really not built for enterprise production scale, but if you use Kubernetes, you can do this as well. You can actually attach persistent volumes to your Docker containers so that if your database, like your container crashes, you don't lose your data for your database, right? It just starts right back up and just picks up the file system, goes to town, right? There's other caveats with that, but just know that while predominantly containers are stateless, meaning you need to have like an external data store that you're talking to for your application that's inside the container, you can also make containers that are stateful. There's just a little bit of extra work to do to make that happen, okay? Now you might say, but Michael, I think you just said that containers are immutable. You said they're read-only, but they have this thin read-write layer. What if I need to deploy a new version of my application? Create a new image. Create a new image, deploy the new version, get the load balancer to talk to the new versions and get rid of the old versions. By the way, if you're using Kubernetes, that just happens for you. Kubernetes is a container orchestration system, and its job is to do what I just described. It's supposed to deploy, manage, load balance, distribute containers. We're going to talk about that in a second. So the main thing I want you to walk away with is that containers are comprised of these layers. They are, immutable read-only. They come from a Docker file, and that container layer is ephemeral unless you add a persistent disk to it, okay? And this is all just application virtualization. That's all it is. All right, so what best describes container images as a result of that conversation? What are we talking about? Are container images ephemeral? I actually think you could probably argue they're ephemeral. Are they immutable? Are they made up of many read-write layers? Are container images running instances of containers? I see a bunch of you putting B, so I think you know, right? I would argue, by the way, that containers, stateless containers are ephemeral, but they're not all ephemeral. So containers can also be stateful. So immutable probably is the best way to describe this because we're talking about container images, not running containers. Okay. Okay, so last thing I'm going to talk about, and then we're going to switch gears back to class content. So I'm just going to run through this one quickly because this gets a little into the weeds. But when you run a Docker file has typically is either sourced from what they call scratch, which means nothing, or it's sourced from another container image. In other words, you can build your application on top of OpenJDK 8 or 11 or 13. Now, I notice this says CentOS 7. By the way, this just has the binaries for CentOS inside of it. It's not actually running the kernel, just FYI. Now, here, there's another instruction where they're running yum, which is just going to install Apache and run an update. Then they're going to expose port 80 like from the container. So the container is now going to listen on port 80. And then they're going to copy this sh file, which is in the directory where the Docker build command is being run. And they're going to copy it from the directory they're in, and they're going to put a copy of it into the container at the root directory at /. Notice every time I do this, this is adding a layer. Then they're going to change permissions on the file they copied into the container. And then they're going to end with a command. It could also end with an entry point. But that CMD is that when someone runs this container, it's going to automatically run that web server like Bourne shell script or bash script. If you run Docker build against this file, it's going to output a container. You can tag the container with whatever name you want, and then you could actually push the container to a registry, like a container registry, and other people could download it at that point in time. So this is how you build a container image that you can then share with other people. If you want to change something about the container image, you change this file, rebuild it, push it out so that someone can get version 2 of your application. Same thing with version 3. Change this, push it up. They can now download version 3. So here, if we're building a Docker file as an example, for example, we'd probably choose node 10, just as an example, because we're building a JavaScript app. By the way, try not to use the tag latest on any of your stuff, because that's going to cause all kinds of problems with development. Then what would happen is that we could set our core working directory. So in this case, user source app. And then from here, we could copy in a package. In this case, we're actually putting in some JSON that we have in our directory, like package JSON, and we're putting it into the container. And then we're going to run npm install because we need to run all our requirements, like we need to install a bunch of stuff, right, for Node. And then we're going to copy over our server.js file that's in our local directory into the container. We're going to expose port 8080, and then we're going to run a node server.js command, right, so that we can actually have the container actually do something. This is all a Docker file. Any questions about what could run inside of a container? Because as you can see, if you can run your app on the command line non-interactively, you can put it inside of a container. So basically anything that will run on the command line, you can stick inside of a container as long as it's not interactive. No, no GUIs and stuff like that. Although, well, you'd be surprised what you can get away with. Okay, that's containerization, process virtualization. You'll hear the words Docker and containerization used synonymously. Docker is just a brand of containerization, like a flavor. They also happen to be the company that gave it to the world, so they made it easy. So it's a little bit like how people are like, I'm going to take an Uber, but they're actually taking a Lyft or something else. So Docker's a good company. Docker hasn't figured out how to monetize those, so they're kind of falling out of favor a little bit. But they have given the world containerization. They open sourced it. They helped create the open container initiative. They helped create container runtimes. They really did actually some good work around this. They themselves just didn't really figure out how to financially survive. Good. Let me just skim one little thing for you, just to make sure this concept is driven home. We're only going to do this for like 2 seconds. So we're almost done. So Kubernetes, by the way, so imagine that you're doing this, the thing we just saw, where you are running containers on top of a single host, but instead you need to run it across 5,000 hosts. This is the problem that ECS and EKS solve. Elastic Container Service and Elastic Kubernetes Service allow you to do this. They allow you to run these hundreds, if not thousands, of these containers across a bunch of boxes. The job of a container orchestration tool is to schedule, place, self-heal, load balance, manage storage, manage security, do some monitoring, and do some logging. So this is what this governs. So Kubernetes, by the way, has an incredible community, is cloud deployable. It does actually use a declarative format, although you can do procedural stuff, but most of the time, you just tell Kubernetes what you want. For example, if we were doing an imperative or in like a procedural format, you would say, go here, go here, go here, and go do this. Instead, with a declarative format, what you do is you just say, look, I want a black rectangle. I want these dimensions. I want you to start the position here. Okay? So Kubernetes is a container orchestration, container management service. ECS, the Elastic Container Service, is Amazon's proprietary container management service. ECS is easier to use. EKS is an industry standard. So you can extend EKS using your same industry standard tools, but ECS is proprietary. So just so you know, that's the difference between those two services. As a developer, if you just want easy, go for ECS. If you need to run Kubernetes because you're running Kubernetes in your data center and you're running Kubernetes on your laptop and you're running Kubernetes in Azure and you're running Kubernetes in Google, you're going to run Kubernetes you're going to use EKS over in AWS. Okay. If you want to know more about this, by the way, these projects are all part of the CNCF. The CNCF is Cloud Native Computing Foundation. Just so you know, they have partnerships with a ton of people. Here's all the people they have relationships with. Here are all their projects, by the way. So Kubernetes is the lower left-hand side right here. By the way, if you're in your career and you're in infrastructure and you're kind of wondering what technologies you probably should pay attention to, it's probably going to be on the CNCF's roadmap, just so you know. Creos, Containerd, which are all kind of like container runtime interfaces, supervisors. We can talk about that more if you want to. Anyway, the CNCF is the kind of manager of open source projects such as Kubernetes, right, as an example. Okay. Questions? Did that blow your minds? Okay. Yeah. All right. I'm going to stop this and then we're going to talk about the next thing.